Welcome back to another video. Hypothesis testing is a method used to make decisions or draw conclusions about a population based on data from a sample. It's like a formal way to test if a claim or assumption, called a hypothesis, about something is true. Imagine we're testing a new type of engine oil that claims to improve fuel efficiency. The company says, "Our oil increases mileage to more than 40 miles per gallon mpg." Hypothesis testing helps you check whether this claim is likely true based on the data you collect from a few cars. When stating a hypothesis, we are usually testing two complementary claims, the null and the alternative hypothesis. The null hypothesis, usually annotated as H-null, is the default claim. In our case, it might be, the new oil does not improve mileage, or statistically, it means that the average mileage per gallon using the new oil is less than or equal to 40 miles. The alternative hypothesis, usually annotated as H-A, is what we want to prove. Here, it's, the new oil improves mileage, or statistically, it means that the average mileage per gallon using the new oil is more than 40 miles. We defined our hypothesis, and, to make a conclusion, we need to collect data. By taking a sample of cars, using the new oil, measuring their mileage, analyzing the sample by calculating the average mileage, seeing how it compares to 40 miles per gallon, we can make a conclusion by using statistical tools to determine whether the observed sample is strong enough to reject the null hypothesis in favor of the alternative hypothesis. In hypothesis testing, how we define our hypotheses depends on the question we want to answer. A two-sided or two-tail hypothesis is used when we want to check if a population parameter, like the mean or variance, is equal to a specific value or not. In this case, the null hypothesis states that the parameter equals the hypothesized value, for example mu0, and the alternative hypothesis states that it is not equal to mu0. This test examines deviations in both directions, meaning we are interested in values that are either higher or lower than the hypothesized value. For example, if you want to test whether the average weight of a batch of products is exactly 50 kilograms, a two-sided test will detect any deviation, whether the weight is more or less than 50 kilograms. Alternatively, a one-sided, one-tail hypothesis is used when we want to test if the parameter is either less than or equal to or greater than or equal to a specific value. Here, the null hypothesis represents the status quo, and the alternative hypothesis focuses on one direction only, either greater than or less than. For instance, if you're testing whether a material's strength exceeds 100 N, a one-sided test would focus only on whether the strength is greater, ignoring any lower deviations. The choice between these tests depends on the research question. Use a two-sided test for detecting any change and a one-sided test when the concern is focused on a specific direction, like improvement or exceeding a limit. Basically, in hypothesis testing, we are studying two different distributions, and we want to decide which one is producing the sample. Before we discuss how to conduct a hypothesis test, there are a few key concepts we need to cover. First, we need to address the errors inherent in any hypothesis test. These are known as type 1 and type 2 errors, also referred to as false positive and false negative errors. Next, we need to discuss the rejection criteria. To reach a conclusion in a hypothesis test, we must decide whether to reject the null hypothesis or fail to reject it. This decision is based on a rejection criterion, which can be determined using either a rejection region or p-values. It's important to remember that the primary goal of hypothesis testing is to reject the null hypothesis, thereby supporting the alternative hypothesis. However, failing to reject the null hypothesis does not confirm its validity. It simply suggests that more data may be needed. Let's go over an example together. Suppose that an engineer is designing an aircrew escape system that consists of an ejection seat and a rocket motor that powers the seat. The rocket motor contains a propellant, and in order for the ejection seat to function properly, the propellant should have a mean burning rate of 50 centimeters per second and a standard deviation of 0.79. If the burning rate is too low, the ejection seat may not function properly, leading to an unsafe ejection and possible injury of the pilot. Higher burning rates may imply instability in the propellant or an ejection seat that is too powerful, again leading to possible pilot injury. So, the practical engineering question that must be answered is, does the mean burning rate of the propellant equal 50 centimeter per second, or is it some other value? It seems that a two-sided hypothesis test to be appropriate, as any deviations in both directions might be catastrophic. Field experts have advised us to reject the null hypothesis if the sample mean is less than 48.5 or greater than 51.5. In the following videos, we will cover how these number 48.5 and 51.1 are typically chosen. We start by defining our hypothesis. In null hypothesis, we hypothesize that mu equals to 50, and in the alternative, we claim mu is not equal to 50. Here, please note that each hypothesis represents a normal distribution centered at the hypothesized mean. Under the null hypothesis, the sample is generated from a normal distribution centered at 50, while under the alternative distribution, the normal distribution generating the sample is centered at a different value. We are assuming these two normal distributions have the same variance, and their only difference is where they are centered. The next step would be data collection. So, we will take a sample and calculate the sample mean. To make a decision, we need to compare the calculated sample mean to the critical values given by the experts, 48.5 and 51.5. If the x-bar is less than 48.5 or greater than 51.5, we will reject the null hypothesis and report that the average burning rate is not 50 centimeter per second. In an ideal world, we would always reject the null hypothesis when it is false, and we would not reject the null hypothesis when it is indeed true. But there are two other scenarios that are possible, each of which will result in an error. In hypothesis testing, we compare the true state of reality with the decision made based on sample data. This leads to four possible scenarios. Scenario 1 represents a correct decision with a probability of 1 minus alpha. It models the case where we fail to reject the null hypothesis when the null hypothesis is true. Scenario 2 represents a correct decision with a probability of 1 minus beta. It models the case where we reject the null hypothesis when the null hypothesis is false. Scenario 3 represents type 1 error with a probability of alpha. It models the case where we reject the null hypothesis when the null hypothesis is true. And finally, Scenario 4 represents type 2 error with a probability of beta. It models the case where we fail to reject the null hypothesis when the alternative hypothesis is true. When we set up the null hypothesis that the population mean is 50, we are statistically assuming that the burning rate of the propellant follows a normal distribution with a mean of 50 centimeters per second. Remembering the properties of normal distributions, we know that their domain stretches from negative infinity to positive infinity. This means that even if the true mean is 50, a normal distribution can still produce sample means that are less than 48.5 or greater than 51.5. Then, why would we reject the null hypothesis, the claim that the population mean is 50, if, for example, the sample mean x-bar is 47? Please take a moment to consider this question. Based on expert advice, we reject the null hypothesis and conclude that the population mean is not 50 if the sample mean falls below 48.5 or above 51.5. We make this rejection as we understand that it's very unlikely for this normal distribution to create a sample which mean is above 51.5, and it is more likely for another normal distribution, for example centered at 52, to produce such values. However, we should acknowledge that, although unlikely, it is still possible to observe a sample mean outside this range from a normal distribution with a mean of 50 and a standard deviation of 0.79. Given the potential consequences if the propellant fails, we are willing to accept this small error and reject the null hypothesis, as it is very improbable for such extreme sample means to occur in a normal distribution with a mean of 50. Looking at the properties of normal distributions, we know that the probability density function peaks at the mean. As a result, it becomes increasingly unlikely to observe sample means the further they deviate from the mean. We can even calculate the probability of observing a sample mean less than 48.5 or greater than 51.5, the blue area, assuming the sample mean follows a normal distribution with a mean of 50 and a standard deviation of 0.79. The blue areas represent type 1 error, the probability of rejecting the null hypothesis when it is actually true. Under the null hypothesis, the mean propellant's burning rate follows a normal distribution with a mean of 50. Although possible, we suspect observing such extreme values of less than 48.5 or greater than 51.5 are highly unlikely, and we assume that a different distribution, perhaps centered at 48 or 52, is generating them. This assumption may sometimes lead to rejecting the null hypothesis even when it is true, which defines type 1 error, typically denoted as alpha. Here, alpha is the probability of observing sample means below 48.5 or above 51.5 when the true population mean is 50. Standardizing these probabilities lead to z-values of negative and positive 1.9, with a summed-up cumulative probabilities of 0.0574. This means that if the true mean burning rate of the propellant is 50, there is a 5.74% chance that we will observe a sample mean outside the range of 48.5 to 51.5 generated by such normal distribution, leading us to incorrectly conclude that sample was generated by a normal distribution centered at a mean different from 50. So far, we have discussed the statistical meaning behind mu equaling to 50 in the null hypothesis. Now, let's examine the alternative hypothesis. When we state that mu does not equal 50, we are considering the possibility that the true population mean is some other value, such as 50.5, 52, or even 49. Essentially, the null and alternative hypotheses represent two different normal distributions with the same variance, but different means. However, these distributions often overlap significantly, making it challenging to distinguish between them. A type 2 error, denoted as beta, occurs when we fail to reject the null hypothesis even though it is false. In other words, we miss detecting that a normal distribution centered at a different value, such as 52, generated the sample and incorrectly conclude the burning rate mean is 50. This figure illustrates the two distributions representing the null and alternative hypotheses. The distribution centered at 50 corresponds to the null hypothesis, while the one centered at 52 represents a potential alternative hypothesis. Our rejection criterion is based on whether the sample mean falls outside the range of 48.5 to 51.5. However, under the alternative hypothesis, it is entirely possible for values between 48.5 and 51.5 to be generated by the normal distribution centered at 52. When this happens, we fail to reject the null hypothesis despite the alternative hypothesis being the main distribution creating the sample. The blue shaded area under the alternative distribution represents the type 2 error, beta. This translates to the probability of our sample mean being between 48.5 and 51.5, when the actual population mean is equal to 52. After standardization, we can see that this probability, which represents beta or type 2 error, is about 0.26. Please note that type 1 and type 2 errors always exist in hypothesis testing, but their values depend on the test design. There is a trade-off between type 1 and type 2 errors. Decreasing alpha, reducing false positives, typically increases beta, raising false negatives, and decreasing beta, improving detection power, typically increases alpha unless we increase the sample size or improve measurement accuracy. We should always report type 1 and type 2 errors. Type 1 error is a key parameter in setting the decision threshold or critical values for a hypothesis test. Typically, alpha is set before the test and is considered a fixed part of the analysis. For example, alpha can be set to 0.05. While type 2 error, beta, is as important, it is not usually directly reported. Instead, it is reported indirectly as the power of our test, which is defined as 1 minus beta. The power tells others the likelihood of correctly rejecting the null hypothesis when the alternative hypothesis is true. Next, we discuss the rejection criteria in hypothesis testing, how we decide whether to reject the null hypothesis. In our example, the cutoff values 48.5 and 51.5 were chosen based on expert judgment rather than a formal statistical approach. However, this is not typical. Generally, there are two main methods for determining rejection. 1. Rejection region, which is a predefined region established based on a chosen significance level, alpha the same as type 1 error. If the test statistic falls within this region, we reject the null hypothesis. 2. P-value, which is the probability of obtaining the observed result, or more extreme cases, under the null hypothesis. If the p-value is less than alpha, we reject the null hypothesis. Both approaches rely on a predefined alpha, ensuring a controlled probability of type 1 error. This is a step-by-step outline of the process for conducting a hypothesis test. Step 1. Identifying the parameter of interest. The parameter of interest is the specific population characteristic we are testing or trying to estimate. It could be the population mean, proportion, or standard deviation. Step 2. Defining the null hypothesis. The null hypothesis is a statement about the population, which serves as the starting assumption. For example, population mean equals to 0. Step 3. Defining the alternative hypothesis. The alternative hypothesis is the opposite of the null hypothesis. It reflects what you are trying to prove or find evidence for. It could be a claim that the parameter is greater than, less than, or different from the value specified in the null hypothesis. Step 4. Choosing the test statistic. The test statistic is a numerical value calculated from the sample data that is used to decide whether to reject the null hypothesis. The test statistic might be a z-statistic, t-statistic, f-statistic, or chi-squared statistics depending on population parameter of interest and availability of data. Step 5. Defining the rejection condition. This step defines the criteria for rejecting the null hypothesis. The condition is based on the test statistic and is often set using a significance level, alpha. The options are the rejection region or the p-value approach. Step 6. Computations. This step involves calculating the necessary sample statistics and substituting them into the formula for the test statistic. Step 7. Drawing a conclusion. Based on the comparison of the test statistic to the critical value or comparing the p-value to alpha, we make a decision about whether to reject or fail to reject the null hypothesis. We need to also interpret this decision in the context of the original problem. Here are the test statistics we use in hypothesis testing. As you may have noticed, these are the same statistics we applied when deriving confidence intervals to make inferences about population parameters. We can use these test statistics to analyze the parameters of a single population based on a single sample, or to compare parameters between two populations using two samples. These statistics are essential for studying population parameters such as the mean and variance. First, you need to identify whether you are dealing with single sample or two samples. Second, you need to identify whether you are interested to studying the population mean or the population variance. If the parameter of interest is the population variance, you are done. Chi-square test statistic should be used for studying the population variance using a single sample, and F-test statistic should be used to study the ratio of two population variances using two samples. Now, if the population parameter of interest is the population mean, you need to also identify how much you know about the population variance. For example, if you want to study the population mean using a single sample, if you know the population variance, you need to use a z-test, whereas if the population variance is unknown, you should use a t-test. To study the difference in means of two populations, you would have 4 options. If the population variances are known, you should use a z-test. If the variances are unknown, the choice of t-test depends on how much you know about the variance and how the samples are collected. If the samples are collected in pairs, you would need to perform a paired t-test. Otherwise, if you can assume the unknown variances are equal, you should use a pooled t-test, and if you cannot make that assumption, you should use Welch's t-test. We will further discuss each of these hypothesis tests in a separate video. Thank you for watching this video.
See you in the next one.